Hi, I'm Asif Ali Khan, PhD student at the Chair for Compiler Construction at TU Dresden in Germany. Today, I'll present our work on data placement strategies for Racetrack memories. And this work, I've done this together with my colleagues at the Chair for Compiler Construction, Andres, Fazal, and Geronimo. So before talking about the data placement, I'll first try to motivate the non-volatile memories in general and racetrack memories in particular. So in here, I'm showing this figure which gives the industrial numbers, the industrial figure for the past few years and a forecast for the next few years, which shows how the market size of non-volatile memories have grown exponentially in the last few years and how it is projected for the next few years. So right now there are quite a few non-volatile memory technologies available, but PCM, which is the phase change memory, magnetic RAM, resistive RAM, and racetrack memory. So those are the few that have got a lot of industrial attraction. If we talk about the capacity of the currently available memory technologies, so again I'm presenting the statistics from 2018, which shows the capacity, and from here you can see that phase change memory has already surpassed DRAM and NAR flash in terms of capacity, and STT RAM, which is the spin transfer torque, magnetic RAM, and resistive RAM, they are also catching up. So as I said, PCM, STT MRAM, and ReRAM, they are the current industrial choices, but there are quite a few other non-volatile memory technologies. So for instance, ferroelectric RAM is very promising, CB-RAM, RRAM, and racetrack memories. So today I'll specifically focus on the racetrack memories, and the reason is because they promise capacity, which is the need of the hour. So racetrack memories can be 10 to 100 times more dense compared to the most dense memory technology available today. With this table, I kind of give a direct comparison of racetrack memories with all other available memory technologies, and as it's shown here. So the cell size, as I said in the last slide, it's the most dense memory technology means it has the smallest cell size. Endurance is not an issue, it's a magnetic memory. Read time is comparable to DRAM. Write time is medium, which is again better compared to other non-volatile memory technologies, and energy is of course better because it's non-volatile. So with this, this shows that non-volatile memories in general are required to overcome the energy barrier of today's systems, and racetrack memory in particular is a better choice amongst other non-volatile memories. In the next few slides, I'll talk about what exactly racetrack memory is, how it works, and how does the overall architecture looks like. So let's start with the introduction. So a single cell in racetrack memory is a magnetic nanowire which can be placed horizontally or vertically on the surface of a silicon nanowire of a silicon wafer, and then the magnetic nanowire is split into multiple domains, which is basically a magnetic region with same magnetic direction. And domains in the nanowire can have one of the two magnetization directions, so we show them by pointing up and pointing down here in this figure, and each domain then represents a data bit, right? So if we talk about data storage, so we can think of, let's say, the downward magnetization direction is representing 0 and the upward magnetization direction is 1. So then that's how the data storage looks like. What is interesting and what is also challenging, which we will discuss in the coming slide, is the accessing data, the data access of racetrack memory. So what happens is magnetic nanowire has more than one data bits, but it has in general, like in the best case, it will have one access port. So there can be more than one access ports, but they are costly. Again, we'll come to them in a bit. But for now, the working principle is that if you want to read a particular domain, let's say this domain here or this data bit here, you have to move it to the access port by applying a shift current. And this movement of domain inside the nanowire is costly because this shifting takes time in the first place, and then because you're applying current, it takes energy, right? So this is the challenging part of the racetrack memory, which is what we actually want to address in this work. So in here I present an overall architecture. So magnetic nanowires, which I showed on the previous slide, they are grouped together to form an abstract, a more coarser unit, which we called domain wall block cluster, which is represented here. So it's a group of nanowire, which is so the nanowires are grouped together in a way that access ports in all nanowires point to the same location, and the data storage is then, data is stored in a way that bits of a variable or of a memory object are distributed across all nanowires. So for instance, if I want to store variable 0, I will have to store the first bit of 0 in the first racetrack, the second bit in the second racetrack, and the t-1 bit in the last or the tth racetrack. And if I want to access then variable 0, I can access all of them in parallel because the access ports are all pointing to the same position. And if I want to access in the next step with v1, I need to move all data bits to the port position, which is pointing to location 0. And because all of them are at the same place in the racetrack, I can move them all in a lockstep fashion and can read all of them in the next step. DBCs are then grouped together to form subarrays, which is the same basic memory entity as in other memory technologies, and subarrays are then grouped together to form banks, and banks are then grouped together to form further higher abstraction modules such as rings and channels. Okay, so in the previous slides we talked about shifts, and we said shifts are costly, but how costly are they? So as I said, so they incur energy and performance overhead, but that's not the only thing. So shifting means that the access latency of the racetrack memory is placement dependent. So if a variable, or if let's stick to a data bit, so if a data bit is stored far away from the access port, it will take longer latency compared to if it is stored closer to the access port, right? And this variable latency is also challenging because it makes scheduling of the subsequent instructions more difficult. That means design of the memory controller. It's evaluated in the previous work, and it has been shown that in the worst case, the shifting plus read latency can be up to 26 times. On average, again, and evaluated at the last level cache, it has been shown that shifting consumes more than 50% of the cache energy. And then there is still another problem. So shifting can incur errors as well. So for instance, a domain or a data bit may not be exactly aligned to the data port. So there are two well-known shifting errors. One is called overstepping and another is stop in the middle. Okay, so shifting is problematic. Shifting is challenging. Racetrack memory is promising. So let's solve the shifting problem, or at least subside it. What are the possibilities? So the first solution, which is straightforward, which is the first one that comes to mind, is increase the access ports. Right. So if you increase the access port, then if let's say I want to access this domain here, I need at most 2 shifts. Right. If I want to access this domain here, I need at most 1 shift, and so on. What next? there is this other proposal of reconfigurable cache which was presented in 2014, which says you can do dynamic reconfigurability of the domains or the data locations, the memory locations, if the cache utilization is not 100%, right? So for instance, in the given example, if let's say you know that the cache utilization is less than 75%, so you can disable out of the 16, you can disable 4 locations which are the farthest from the access port, right? Again, if again you do the cache, you measured the cache utilization and you found that the cache utilization is less than 50%, you can further disable the position which are farthest from the access ports and so on. Another solution is what we call pre-shifting. So the intuition in here is similar to prefetching. So in prefetching, you access data from memory proactively, and pre-shifting is basically the same thing, but instead of fetching data, you align data to the port positions proactively. So that's why we call it pre-shifting. And there are still other possibilities. For instance, this data migration, which means so you monitor the utilization of each location inside an NOR, and if you know that the location which is farthest, the data element which is stored in the farthest location is accessed quite often compared to the data element which is stored closer to the access port, so you can swap them. You can swap the position. Right. So all these are hardware solutions which are very promising, but the problem is that all of them are expensive. Right. So they takes, in the first place, so they take energy, and secondly, they take the chip budget. Right. So which means if you introduce this additional hardware, you have to compromise on capacity, which is something which we don't want. So considering these hardware solutions are that they have overhead, so there are still software solutions. So for instance, this data placement, if we look at the data placement, so consider this very simple example where we have 5 variables and the memory trace shows how those variables are accessed in an application. And if we talk about the placement of these 5 variables in memory, so you have many possibilities, many permutations. So let's take a random permutation. So let's say we store it in this order: A, E, B, F, C, D, and then we took another placement, which is another permutation of the same variables. So if you talk about the memory technologies available today, it shouldn't matter, right? Because all 5 variables are in memory. So that means if we need them, we'll get them from the memory. But from the perspective of the racetrack memories, if I compare the shift cost, which is actually basically the number of shifts in the 2 placement, it's significantly different. So in the first one, I will incur 51 shifts. In the second one, I'll incur 21 shifts, which means 200 times less shifts compared to the first one. Right. So data placement is, so this shows that data placement is promising. So in the previous slide we talked about single DBC, but if we talk about multiple DBC, it becomes more interesting. So we take a slightly bigger example with 9 variables instead of 5 and in a bigger trace, and we talk about the placement again, but now we have 2 decisions to make. The first one is where to place a particular variable inside a DBC, and the second decision is how do we distribute variables across DBCs, right? So I have again one placement with some distribution and some placement within DBCs, and I have another placement, and again if I compare the shift cost, they are significantly different, right? So the second placement is more than 3 times better compared to the first one. So to talk about the solution, so the previous slide shows that data placement is promising, but talking about the solution, so this single DBC or intra-DBC placement of variables is pretty much solved, or at least there are some solutions available which are very promising. I won't go into the details of all these solutions. I just want to emphasize on the net results at the bottom line, which says that shift reduce which is this heuristic here, is better compared to other existing heuristic. Talking about the multiple DBCs or variable distributions across DBCs, which is what we call inter-DBC placement. So there is a heuristic proposed by Chen et al. In this paper presented in or published at TULSI in 2016. And the way it works is that it takes all variables, so all 9 variables, and it sorts them based on excess frequencies. Excess frequency is the number of time a variable is accessed in the memory trace, right? So for instance, A is accessed the most in this trace compared to all other variables. How exactly? We can see that in the next slide. The second most access variable is E. So E is placed again at location 0 in the next DBC. So in this example, as I said in the previous slide, we talk about 2 DBCs and distribution of 9 variables in 2 DBCs. So the first variable goes to the first DBC, second goes to the second DBC, third goes to the first one, and so on. And the assumption is that access ports are all at location 0. And the intuition is that because these variables here at lower locations, they are accessed more frequently, so we have to place them closer to the access port, right? So that's the main idea. But when we did our analysis of the bigger traces and real world applications, we found that access frequency alone are not sufficient to decide where to place a memory object in which DBC and where exactly within a DBC. And we found that if you do the lifespan analysis or timing analysis of variable objects, of the memory objects, you can come up with better memory layouts. And that's exactly what I'm going to talk about in the next slides. So again, we take the same trace, the same memory trace from the previous slides, but now we include the timing information. So the index here basically shows the timing, how the variables were accessed in the trace. So for instance, A is accessed at some time instant which is less than the time instant of B. So that means A is accessed before B, and then this B is accessed before this second time access to A, and so on. Based on this information, so we do the analysis to find the first occurrence, which we represent with FV, and the last occurrence of a variable, which we represent with the LV, and of course we do the access frequency analysis, so we represent it with AV, and in here we show that A is accessed 5 times. First time it was accessed, so at the first time instant, and its last access is at time instant 11. The same is for B, C, D, and based on this information, so we found that variables which are disjoint in their lifespans, if you separate them from the list of all variables, you can significantly reduce the number of shifts, because, so for instance, A is disjoint to all variables which are first accessed after 11. So for instance, this E, F, G, and so on. So A is disjoint to E. So if you place A and E in the same variables, of course by maintaining the access order, so if you go from A to E, you will never come back to A, because A is the last instance of it was already before the first instance of E. So we define the first the disjointness. So we say variables X and Y are said to be disjoint if the first occurrence of variable Y was greater than the last occurrence of variable X. And there may be many possibilities, or maybe many combinations of disjoint memory accesses, as I said. So A is disjoint to E, E is disjoint to H. So one combination, for instance, will be A, E, H. Then there can be other combinations. So for instance, A is disjoint to F, F is disjoint to G, G is disjoint to Yeah, so A, F, G, and so on. So to decide which combination do we pick to place in a DBC, so in there we actually use the axis frequency information, right? And based on the information from the axis frequency, we pick the right combination. Let's look at the same example, and see how it works. So as I said, we take all the information that we have and we sort all variables based on their first occurrences. So for instance, A was accessed initially at location 0, at location 1, so it's 1. The first occurrence of B is 2, and so on. So we sort all variables based on their first occurrences, and starting from the first variable, we pick variables one by one and assign them to the DBC, which is dedicated for these disjoint variables based on the information which is the following. So if the axis frequency of variable A is greater than the sum of axis frequencies of all variables which are accessed in the lifespan of A, so then we pick A, right? Otherwise, we drop A and move to the next element. So for instance, in this case, the axis frequency of A is 5, and the axis frequency of variables which are accessed in the lifespan of A, which are B, C, D, so the sum of axis frequency of B, C, D is 6, right? So we drop A and pick B, C, D and assign them to the DBC, which is dedicated for disjoint variables. Then we continue doing the same for the rest of variables. So for instance, we come to E and we do the same analysis. The axis frequency of E is 3, and then if we look at the lifespan of E, so E starts at 13 and it finishes at 18. So now there are two possibilities. So for instance, one possibility is that we only compare two variables which starts and finishes in the lifespan of E, which is the case of F, or we pick variables which starts in the lifespan of E but finishes outside the lifespan of E. So, right, so if that is the case of F and G, G starts in the lifespan of E but it finishes outside the lifespan of E. So in this case, we actually compared both heuristics and we found that the first case actually gives better results in terms of the number of shifts, right? So now we have a straight comparison. The axis frequency of E is greater than the axis frequency of F, so we pick E and drop F, and then we continue doing the same. We compare the axis frequency of F to G, which is less than. So basically the lifespan of, yeah, so we dropped F already. You cannot place F here because then it of course interferes with E, so then it's not disjoint anymore. So we go to G. G is already outside the lifespan of inside the lifespan of E, so it's not disjoint. So the next disjoint variable is H, and we pick H and put it in the DBC dedicated for disjoint memory accesses. For all remaining variables, in here we have an example of 2 DBCs, so we pick all of them. We pick all of them and store them in a separate DBC. But if we have more than 1 DBCs, then we do the axis frequency based distribution similar to the baseline chain heuristic. And on all these DBCs which are assigned based on AFD, we apply the intra-DBC solutions which I showed in one of the slides, the chain heuristic, shift reduce heuristic, and chain tiebreak heuristic. Okay, so with this I'm moving to the results. Let's see how it looks like, but before, let me talk about the experimental setup. So we take the offset stone benchmark suite, which is in total 30 benchmarks. For the Racetrack memory simulation, we use the Racetrack memory simulator RT-Sim, and we evaluate the following configuration. So we take the AFD, the axis frequency based distribution, without intra-DBC optimization. So if U is the order of first use, which is the order in which they appear in the memory trace. Then we take the disjoint memory axis, the one that I just presented, without intra-DBC optimization. Then we take DMA, the disjoint memory axis is with the chain intra-DBC optimization. DMA with shift reduced intra-DBC optimization, and we formulated a genetic algorithm to see how far the heuristics are from the genetic algorithm, which is supposed to be closer to optimal, and we evaluated a random walk. Okay, so here is actually a summary of the overall results. So there are a lot of results in this one slide, but I'll try to make them step by step, to explain them stepwise. So let's first talk about AFD and DMA, right? So the direct comparison, that AFD is represented with circle and DMA is represented with triangle. And if I look at the results in this figure or in this zoomed in version, so in all cases triangles are closer to the baseline, to the normalized baseline, which is the genetic algorithm results. So all costs are normalized to GA, which is 1, and yeah, so minimum in here, so this is the cost, so minimum is better. So if you look at the triangle, they are closer to the GAs, and if I look at the circles, in almost all cases, just let's pick one of them. So they are, so the first circle appears here, and all of them, the rest are outside the zoomed version, right? So they are above. If we talk about the number of DBCs, so smaller circle means less DBCs, bigger circle means more DBCs, and again, as it's shown in the figure, so the bigger circles are closer to the GAs compared to the smaller circles, right? And the idea is that if you increase the number of DBCs, the number of shifts automatically decreases, because then you have less number of variables per DBC, right? And so on. So for the random walk, which are all on top, so it's the worst results. We executed it for 60,000 iterations. And as I said, so DMA, the disjoint memory accesses, this heuristic performs better compared to the FD. Talking about the energy results, so again, it's the energy consumption normalized to the axis frequency distribution with no intra-DBC optimizations. So in here again, it's the consumption, so smaller is better. So DMA OFU is better compared to AFD OFU, and DMA shift reduce is better compared to DMA OFU, which is, that means the intra-DBC optimization further improves the energy. The same for 4 DBCs, and the same trend for 8 DBCs, and the same trend for 16 DBC. The interesting thing probably which we need to observe is the increasing trend in the energy, which is due to the increase in the leakage power, as is obvious from the figure. DMAs are consistently outperform all other configurations. For the latency, again, we compare to the axis frequency based distribution with no intra-DBC optimization. DMA OFU is better compared to FD, and shift reduce further improves the number of shifts. And again, as I said, it follows the same trend. The improvement in here is less compared to the improvements in less DBCs. And as I said on the previous slide, so if you increase the number of DBCs, that means you store less number of variables per DBC, so you already have less or small room for improvement. So that's why the improvement is not so significant. Okay, so that brings me to the conclusion of my presentation. RTMs, they're promising. They promise capacity, latency, and energy, but they have shifts which can be mitigated by deciding some optimized layouts. But deciding those layouts, they are again tricky. In the existing solutions, people proposed and used axis frequencies, but we showed that axis frequencies alone are not sufficient. If you combine the timing information with axis frequency, you can decide and find better or efficient layouts. In the future work, we're planning to do the distribution of memory objects, the uniform distribution of memory objects across DBCs. So the heuristic in its current shape is that it separates disjoint accesses from non-disjoint accesses, and in case you have only one disjoint variable, it will go to the dedicated DBC, which means you will not be using the rest of the places, the rest of the location. So we are planning to come up with a better solution, and we are in the next step try to develop generalized RTM specific compilers. So with that, I would like to thank you